Okay, hello guys. We are going to continue our lesson on Newton methods. So this example 2, given the function f(x) equals to cos x plus x equal to 0, has a real roots in the interval negative pi over 2 to 0. Approximate the root of f using A. iteration method, B. Newton-Raphson method, using x0 equals to negative pi over 4 as starting point. Give your answers correct to significant figure. So in this case, let's recap how are we going to use iteration method. Before that, since it's already stated here that has a real root, so it means that you don't have to check whether the roots lies in the interval or not. So we know that the interval lies in that particular given interval. So in iteration method, so what we do first, we have to establish the relationship such that the next iteration will give the better approximation of the root. So in A, so let's establish that relation first. So from here you can write down x equals to negative cos x. So from that you have xn plus 1 equals to negative cos xn. Okay, alright, so let's use this straight away. So for x1, when n equal to 0, so you have negative cos x0, okay, which is equivalent to negative cos, so x0 is given by negative pi over 4. So from here you will get the answer if you do your calculation. So you get 0.7071. I keep it to 4 significant because we want our answer to have to 3 significant figure. Alright, so let's continue on. So x2 equals to negative cos of negative 0.7071. So if you calculate this, you will get negative 0.7602. Okay, so just continue. Okay, let's see what we get here. 0.7602, so equivalent to negative 0.7247. So x4, so for x4 you substitute the value, okay, 7247, so you will get negative 0.7487. So x5 cos negative 0.7487 will give you negative 0.7326. Up until x5, you can still see that the value is still changing, going up and going down, going up and going down. So never mind, but it seems that it kind of like bounded by a certain value. It's still in the range of 0.7 something like that. So we might want to continue more. So if you continue, so you can see that this one is 0.7326, so you will get negative 0.7434. okay, so you can see the value here. You can see this one, so and this one to this one. So you can see that somehow it looks like it's going to a value there. So let's just continue. Let's see how far it will go. So cos negative 0.7434 will give you negative 0.7362. okay, next x8 will give you, so just repeat this, 7362 will give you negative 0.7410. so x9 substitute 0.7410, go to negative 0.7378. okay, so let's continue on. We have negative cos of negative 0.7378 will give you negative 0.7400. So x11 will give you cos negative 0.7400, will give you negative 0.7385. okay, continue on. Negative cos negative 0.7385 will give you negative 0.7395. It looks like it's much more similar now. Okay, so let's continue. So when you continue on, you get cos negative 0.7395, give you negative 0.7388. So x14 give you negative cos of 0.7388. We give you negative 0.7393. x15 we give you cos 0.7393, we give you negative 0.7389. x16 you have negative cos 0.7389, we give you negative 0. So this is 0.7392. so x17 we give you negative cos of negative 0.7392, negative 0.7390. now it's getting closer now, so this one cos negative 0.7390 give you negative 0.7391. so x19 you have negative cos negative 0.7391, which is negative 0.7391. so now you can see that this two value have achieved the same accuracy. So therefore we can say that x approximately negative 0.739 is the approximation, okay, approximated root. Okay, now by using the iteration method, you can see that you need to go up until x19 iteration in order for you to get the approximated roots. So let's see how Newton methods did for this. Okay, so in Newton methods, so you need to have the relation such that xn plus 1 equals to xn minus f evaluated x as n over f prime xn. So first of all, you need to determine your f prime. Okay, so your f prime, so what is your f? So this is your f. Okay, this is your f. So from here, so f prime x is equals to negative sign x plus 1. So that is your f prime x. So now let's continue. Okay, so x n plus 1 equals to xn minus f xn over f prime xn. So for x1, so you have x0 minus f x0 over f prime x0. So what is this? So this is negative pi over 4, okay, minus, so what is f x0, which is cos negative pi over 4 plus negative pi over 4. Okay, because f naught is just you just substitute pi over 4 here and negative pi over 4 here. Okay, so how about the f prime x naught, which is given by negative sign of negative pi over 4 plus 1. So if you calculate this correctly, you will get 0.7395. Okay, so x2. So now your x naught become negative 0.7395. You have to minus cos of negative 0.7395. Okay, then you plus with negative 0.7395 over negative sign negative 0.7395 plus 1. So if you calculate this, you will get negative 0.7391. So you can see that Newton method, after two iterations straight away, we have the same what we have achieved in our iteration method, which is considerably faster, way faster than iteration method. So Newton method is a really powerful method that give a rapid convergence in this case. So let's try to do one more. So 7391 minus cos of negative 0.7391 plus negative 0.7391 over negative sign of negative 0.7391 plus 1. So if you do this, you calculate, be consistent in your calculation, you get 391. Therefore, x approximately negative 0.3739 is the approximated root. Okay, so now you can see already that how a Newton methods works, and it's faster. Okay, it's just that the problem with Newton method is that you have to find the first derivative of a function, because this is just an example where our function is a very simple function, but sometimes when your function is quite complicated, then finding the f prime x is really a problem. Okay, so that is the disadvantage of using Newton-Raphson method. You have to find the first derivative. So I think I stop here. Just a quick example, this lesson. So make sure you know how to apply the Newton method. Okay, so we'll discuss more about the convergence rate and so on in the class. Okay, so I stop here.